we will continue with where we left off in lecture 10. Let us look at the problem that we are considering that led us to what we need to discuss today. First, we considered a functional that is j, whose integrand depends on the unknown function y and its first derivative, second derivative and up to n derivatives, and we wrote the general differential equation and the boundary condition. So, this is the differential equation and these are the boundary conditions. Okay. So, this is the most general form when you have only one unknown function y of x and integrand depends on n derivatives of that unknown function y of x. We were thinking about a case where there can be more than one unknown function. We were specifically looking at a problem where the integrand is a function of y1 and y2, two functions. When you have that, the differential equations and boundary conditions remain the same. In other words, if I say there are multiple functions, I will put a bar on top of it to indicate that this one will be like an array where there will be y1 of x, y2 of x and so forth, let us say ym of x. Okay. There are m unknown functions. How do these equations change? So, then we will say that each one of them will be bar over that. That means that there will be m functions y1, y2 up to ym. Then all we need to do a change here is to add a subscript k there and say k goes from 1 to up to m. Likewise, we have to put k there and this also hk there and it will be k 1 2 up to m. So, nothing else changes. So, when you have multiple functions that are unknown, you will get as many differential equations as the functions. So, differential equations now will be more. So, these are differential equations, differential equations. We will have m differential equations. Now, corresponding there will be m sets of boundary conditions. I say sets because the boundary conditions themselves will be n. If you have n equal to 1, meaning that you have only up to y prime, then we will have only one boundary condition. If it is y double prime, we will have two of them, j equal to 1 and 2, because now n, that is number of derivatives that integrand depends on, there will be that many boundary conditions. So, when you have m functions, all that changes is that there will be m sets of differential equations and then there will be m differential equations, m sets of boundary conditions. Sets apply to boundary conditions because there will be as many as the number of derivatives that are there. Okay. So, this is what we were discussing, and what we tried to consider was a functional where the integrand was supposed to contain two functions y1, y2 and then y1 prime, y2 prime and so forth, any number of derivatives dx. Okay. So, in this context we should note that when you are dealing with two functions, you can still have an unconstrained minimization problem, meaning that whatever we have considered this type of problem, this is unconstrained, right. So, there are no constraints here, unconstrained minimization, right. But then when there are two functions, we can have a constraint also between them. That is the example that we were looking at, but you can also have with two functions unconstrained minimization also. Let us briefly look at that before going back to the example or formulation that we were looking at. Let us find an example of a problem where there are two different functions y1 and y2 and there are no constraints. So, such a problem, let us look at it physically. So, if I have let us say a beam which is fixed at one end, free at the other end. Let us consider another beam. Okay. Let us say this one may be supported with a pin joint over there, and let us say pin joint with a slider at the other end. Okay. There are two beams here, and we can connect these two with a spring. So, a spring constant K. So, now we have here normal x1 is 0 and then x2 is L. So, this is 0 and let us say this x2 is L, that is lengths of both the beams are the same L. So, our domain for the problem is x1 equal to 0 to x2 equal to L, and what we want to find out is how do these beams deform if there is some loading. Let us say on this beam there is some kind of a loading, let us call that Q1 of x. Let us say there is some kind of a loading Q2 of x on this second beam, both of them x goes from here. So, this x goes from 0 to L, and we need to get how does this deform. Let us say that deforms like that, and this might deform like this, let us say. Now, let us call this function not y. Normally for beams we denote it with w. Let us say this is w1 of x is its deformation, and this deformation is w2 of x, meaning at any point from its neutral plane to the deformed profile, that is w1x, and this one is w2x. Okay. Now, if we use the principle of minimum potential energy for this problem, so principle of minimum potential energy, okay, that means that we would like to minimize this. So, I would write minimize potential energy for this beam. Okay. Then we have to minimize with respect to two things. There is the top beam whose deformation is w1x and bottom beam whose deformation is w2x. Both of these becomes our unknowns or variables. So, w1 of x, w2 of x, two functions, that is what we are looking at, right. So, we are looking at a case where there will be two functions, okay, y1, y2, now that became w1, w2. So, that we can write from 0 to L. Yeah. So, we have potential energy of the two beams and the spring we have to include. So, I would say potential energy of beam 1, that is this is beam 1, and then we have beam 2. We have to write potential energy of beam 2 and potential energy of the spring that we have there. Again recall that potential energy is strain energy plus work potential. Keeping that in mind, we can write this potential energy here as for beam 1 it is 0 to L. If I assume Young's modulus is E and second moment of area is I, then W double prime, this is the first beam. So, W1 double prime square divided by 2, that will be the strain energy for beam 1. So, that is strain energy, and the work potential is the negative of the work done, that will be 0 to L. Q1 is the loading acting on it and W1 is the displacement. This will be for beam 1, and then we will have 0 to L E I. In fact, we can call it I1 and I2. We are taking the same material, but moment of area could be a different function. This will be W2 prime square by 2 dx minus 0 to L Q2 W2 dx. Okay. So, this is for beam 1. So, this one is for beam 1 potential energy, and this one is the potential energy for beam 2, and then we have the potential energy or strain energy work potential. Spring does not have a force, so it is only strain energy, that is going to be half. If we say this is a midpoint where the spring is attached, okay, let us assume that this is the midpoint, that is L by 2. So, the extension of the spring, so K times extension of the spring square, so that will be W 1 at L by 2, okay, minus, anyway we are going to square, whichever we write does not matter, W 2 L by 2 square. Okay. So, this will be for there is no work potential for the beam. So, this is for the spring, So, there is spring. So, if you look at this potential energy, now if you look at the terms that we have, that is this first term, second term and third term, they depend on two functions W 1 and W 2. So, that is what we were after. So, you can have problems involving two functions without constraints. In mechanics, geometry, one can think of problems of that kind. So, now moving ahead, we go back to the problem that we are considering, where we took a bar optimization problem, where we had let us say a bar that is fixed, and this is the neutral axis or axis of the bar, and we want to optimize the area profile of the bar, okay, area profile of the bar, which we said A of x, that is one variable for us, and then there is deformation, axial deformation. So, U of x is axial displacement or deformation. Actually, displacement is more correct because points will be moving. So, axial displacement function for some given force P of x, this is the axial load or force applied here. Such a thing, if we want to minimize the volume of this bar or minimize the, let us say, strain energy in this, that is the problem we were considering the last lecture. So, again if I go from 0 to L, that is x 1 is 0, x 2 is L, and x goes like this to define all these functions A of x, U of x and P of x. When you have that, so we want to minimize strain energy, which will be E into A into U prime square by 2 dx. A of x is our design variable here. We want to come up with the optimal area of cross section to minimize strain energy. So, this one is strain energy of the bar under the given load P of x. Now, U prime we said is a state variable. A state variable should be governed by governing equation, which we had derived in the last lecture. So, subject to, we have this E A U prime prime that came from Euler-Lagrange equation, and P is equal to 0, and we also had a volume constraint. So, we had a constraint that 0 to L A dx minus V star is equal to 0. We can also write it as less than or equal to, as if there is an upper bound on volume, meaning you cannot use more material than V star. So, if you look at a problem like this, this has two constraints. So, there is a constraint here which is volume constraint, and here is a constraint which is the governing differential equation, governing differential equation. Okay. There are two constraints, and in all these problems we should very clearly write what is data. For this problem, what is assumed? Here Young's modulus is assumed, length is assumed, and the loading P of x is assumed, and V star is assumed. We have to write this data in such a way that once you say what is known or assumed, the rest of them become variables. So, if you scan through the problem, A of x, that is a design variable, and A again appears here, and rest of it is known, right, and then U, of course we do not know because that is not in the data. So, A and U are two functions that we do not know, that is what we are looking at. When you have two functions, they can be governed by the constraints. There can be cases where there are no constraints, which we already considered in this lecture, how to pose a problem that has two functions, but no constraints. Now, we are looking at a problem where there are two constraints when there are two functions. These constraints, one of them is a differential equation, other is just an integral or functional. This is the functional type of constraint, this is integral type of constraints. These are the two things that we need to discuss now. When you have an objective which is a functional and then a constraint which is a functional. So, this is a functional constraint, that is what we will discuss, what happens if it is there, and then we will discuss what happens if it is in the form of a differential equation. That we will discuss in the next lecture. This is for the next lecture, and this is what we will discuss next right now. Okay. This is a structural optimization problem in its simplest form. Okay. So, let us write out this problem in a general way. Let us say minimize a functional j in our usual way. We will not say 0 to L, we will say in a general form x1 to x2, where this f depends on, let us say y1 and y2, let us say, and its derivatives also. To begin with, you can say y1 prime, y2 prime, and so forth dx, and there will be two functions y1 y2 subject to, okay, we have a constraint of the form of a functional constraint k, say 0 not 0 to L, we will say x1 to x2, x1 to x2 integrand g, that can also depend on both functions and its derivatives. Okay. If you have a problem like this, how do we solve, right? So, in these cases we have to recall what we had considered earlier, which is called the concept of variational derivative. Okay. So, for concept of variational derivative, let us write down what that means. This is something that we had discussed, I think it was in lecture 8, variational derivative. Okay. What that meant was, if I have a functional like j or k, does not matter which one, if you want to, let us say I have a function x and y of x, it can be y1 y2, let us say 1 y of x, let us say that function looks like this in an interval x1 to x2. Now, if we make a small perturbation at some point, let's call this point A, if I make a small perturbation, that point that is there, I pull it up here, right. What that means is that there will be a little change in the function becomes like this. So, because of this changing at a particular value a in the function y, what will happen to j? That is change in this. So, if I say j, in fact we do not need to take two functions right now. So, we can take only one function, let us say one function I have taken. So, we can knock off this for now for our discussion. for our discussion this does not, it is not needed. So, if I take this change, because I have made some change in y, what happened to change in the functional. So, what we do is we have this y plus we have this h, right, j with y, and then there is a little h which we call a perturbation. Unlike the previous perturbation or variation we called, which is effective everywhere in the domain, now it is effective only at particular value a. If you have that and you subtract out the original one without that thing, this we had said can be written as the variational derivative delta j by delta y. That is how we write this variational derivative, which is evaluated for this x at a particular value, right. So, that means that if I were to change the function y of x at a particular value in the domain, let us say a, what is the change in this? Delta j is what we are writing, this plus let us say some small error times delta sigma is what we had written, right. So, this delta sigma is this area. So, this little area that we have, just imagine that this red curve is like a rubber band, at x equal to a you have pulled it up, right. Then there will be a little extra area, that is delta sigma, that is delta sigma. This is some kind of an error because we put an equal to sign here, error term, because the first variation is like a first order term. That first order term we wrote it in this form, then this becomes a variational derivative. This will be an expression, x equal to a there will be some value to it, x equal to b, let us say another point I take there will be different value. As I move along the domain from x1 to x2, this expression delta j by delta y will keep changing. What is this delta j by delta y? This is nothing but, as we had discussed in lecture 8, nothing but Euler-Lagrange equation. In the Euler-Lagrange equation there will be something equal to 0, that something is an expression true for every value in the domain, that is what it is. So, if we have only the function y and y prime, Euler-Lagrange equation will be dou f by dou y minus dou f by dou y prime prime. Okay. So, that is what is this variational derivative, that is what we will use now in order to do this problem. So, let us rewrite this problem in a way that is convenient for us with only one function, because when there is a functional constraint we can optimize the problem even with a single function, meaning I can have an integral which is x1 to x2 where my integrand is dependent on y, only one function y prime. There can be more derivatives also, for now we will write y will be there, and then I have this subject to a k which is also from x1 to x2, integrand is j g, and then y prime dx minus well that is equal to 0 we can take. Let us see what we wrote earlier. So, actually we did not write anything, it is a constraint, means that we have to say this is equal to 0. Okay. Likewise here we will write this is equal to 0. Constraint means there should be an equation or an inequation or inequality. Let us say we take equal to 0. If we have a thing like that, we want to find out what are the necessary condition for this. If it is only unconstrained, we know what it is, we have to write the Euler-Lagrange equation. How do you do with the problem where there is a inequality constraint? So, this is inequality constraint of the functional type constraint. This is the functional type constraint. It is also called global constraint, global type constraint. It is global because this applies to the entire domain to x2, not just a point, which we will look at, as I said, in the next lecture, because in our bar optimization problem, let us go back and look at it. When we wrote the bar optimization problem, we have this which is a global constraint, whereas this is a governing differential equation which should be true for all values of x in the domain x1 to x2. That is a local constraint, locally it should be valid, whereas a volume constraint such as the one we have here is a global constraint that pertains to the entire domain from 0 to L. Okay. So, now let us look at a global type constraint. When you have that, whenever we have to say we are minimizing j, an objective function here, to find a certain y star of x, that is our unknown function. How do we know it is a minimum? We have to check around that function in the function space to see if it is a minimum. Now, how do you check? Whenever you perturb your constraint, which should be 0 here, equality, when I perturb y a little bit, this integral x1 to x2 g might not be 0 with your perturbation. In fact, usually it will not be if you perturb only at one point, right. Then you cannot say that j for that y, perturbed y is less than this, and hence y star is not a local minimum, right, because it is not a feasible point, meaning that whenever a constraint is there and you do not satisfy it in our perturbation, you are not doing it right. So, what we will do now is not have one perturbation, but we will have two perturbations. So, if I have, let us say our function y of x here, okay, let us say the function is something like this at x1 and x2, we choose 2 points. Let us say there is an A and there is a B, 2 points. Okay. Okay, now we have 2 points A and B. We take 2 points because even after perturbation, let us say we write this change in k, that is delta k, there are 2 perturbations. So, where we have to write this variational derivative delta j by delta y, this is the perturbation done at A, plus we had, let us say, error in that epsilon A times delta sigma A, that is delta sigma A is this one, right. So, this is delta sigma A, plus we have the second perturbation with the variational derivative defined at x equal to b, plus error there epsilon b times delta sigma b, and this area is delta sigma b, the total thing should be equal to 0, right. We need to do 2 perturbations so that the constraint remains equal to 0, that is, it is satisfied. When we do this, just like we had done finite variable optimization, we will be able to express one perturbation in terms of the other, that is what we will do. So, we will say delta sigma b here can be expressed in terms of delta sigma A. Then we will take the similar one for j and try to come up with the concept Lagrange multiplier for this problem. We will take it up in the next half.